Hello everybody and welcome to this review video. Remember, in the review video, the goal is for you first to attempt the problem on your own. Then after you've attempted the problem, unpause the video and you can check your work against my guided solution. So if you would right now, pause the video, attempt problems A, B, C, and D, unpause when you're ready to check your work. So zooming in here, our prompt is to find each of the shaded areas under the standard normal curve. So we know we're dealing with the standard normal curve. We'll need to get our table of values out for this particular normal curve. So here I've got my cumulative normal distribution chart, and I want to find remember the way the chart works is it always gives you area to the left of a z-score. So for instance, if I want to find the area to the left of 1.32, I need to go to the second page. I find the row of 1.3, the column of 1.32, and that's specifically the value, when I zoom in, 0.9066. So if I was to quickly sketch that, if I've got 1.32, everything to the left of that is 0.9066 amount. Next, I want to find how much is to the left of 2.54. That's to my second value. So we'll zoom back into our chart. So I'm looking at 2.5, which is this row. 2.4 is this column. Zooming in. And we see it's 0.9945. So if I just sketch that as well. And then the way we deal with in-between values is we take larger value minus smaller value, 0.9945, minus 0.9066. Type that in the calculator and you would get 0.0879. So that's our answer for part A. Let's continue on to part B. Now in part B, I'm only asked to find the value to the left of the z-score negative 1.92, so that's just a direct application of the chart and no other step needed. It is a negative z-score, so I go back to the first part of the chart. Negative 1.9 is this row, 0.02 is this column. I can see that value is 0.0274, and that's my answer. Now here, I see I'm asked to find the area to the left of this value and to the right of this value. And one other thing that I remark on is the values are symmetric, negative 0.99, positive 0.99. So because the normal curve is symmetric about the middle value at 0, I know the area that's before this curve is the exact same as the area that's after this value. So all I have to do is find one of it and double it. Now in particular, I know the way the chart works. The chart tells me area to the left. So I want to find the chart value for negative 0.99, and then that area is what will be here to the right of positive 0.99 by symmetry. So negative 0.99, I've got my negative 0.9 row, my negative 0.9 column, and we see that's 18.67. That's the same value to the right, and then 2 times 0.1867. Y'all might have already caught this. I apologize. There's an error there. My line was skewed. I did not mean to make this error, but hopefully this can show us the importance of making sure you're reading the chart correctly. Do you see I started at the correct row, but then my trajectory kind of peeled down to the second row, which gave me the wrong value, which would have gotten this whole problem wrong, even though I had the right concept. I've got to watch my details. This is the negative 0.9 row. This is the 0.99 column. So as I zoom in here, I see the value is 0.1611, not what I said earlier. So let's correct that. You probably were wondering what I was doing wrong. So now we've corrected that. We also need to correct this value. So make sure you're not skewed as you're looking through the chart. 0.3222. Great. So that is the area shaded both to the left of negative 0.99 and to the right of 0.99. Now part D, I see that I'm asked to find the area to the right. I'm cautious because I know that area to the right is 1 minus the number in the chart, because the chart always gives you area to the left. And remember, the total area under the curve is 1. So if the chart is going to give you this value, but you want to find this, you need to do 1 minus that number. So let's find the amount of area that would occur to the right of 0.72 from the chart, and that's what we'll subtract from 1. So 0.72, my row for 0.7, here I'm going to make sure I don't get off on the row. My column for 0.02, so that's a value of 0.7642. But then that's what I want to subtract from 1. And we would get 0.2358 as our answer. So we've got our next problem. As always, pause the video right now, attempt the problem on your own, unpause to check your work. So here I'm asked to find the z-score. I know z-score is related to my cumulative normal distribution chart that we've been working with to this point. So I'm going to draw my sketch of the normal curve. And we want to find the z-score for which the area to the right is 0.84. Now remember, key idea, the area under the entire standard normal curve, or normal curve is here 1, standard normal, excuse me, is 1. The chart gives you area to the left. So if the area to the right of the value is 0.84, the vast majority of the total area, that means your z-score actually has to be before the 0 mark, because at 0, you've got exactly half to the left, half to the right. So if the area to the right is bigger than a half, that means you actually have to be on the negative axes. So here's my unknown z-score. But what I know is that the area to the right is 0.84. But that means the area to the left, the value the chart actually gives me, is 0.16. Now, how does the chart come into play? It kind of comes into play in a reverse way. What I would do now is I need to look in the middle section to see, okay, when am I seeing a value of 0.16 as close as possible, and then find that corresponding z-score. So I go to the portion of the chart that has my negative z-scores because I know I'm before 0. Let's look for something closest to 0.16. So here I've got a 0.161, 0.5187, so I'm a little before, a little after. We go for closest in absolute terms, so the 0.5187 is about 0.0013 away, whereas the 0.1611 is only 0.0011 away. So this is the closer one. So we figure out the z-score attached to it. It's from the row of 0.99, the column from 0.09. So that means the z-score is negative 0.99. And that would be our answer. So our next problem is on the screen. Pause the video now, unpause when you're ready to check your work. So here I've got a normal population has a mean of 47, population standard deviation sigma of 3. For what proportion of the population, what proportion of the population is between 40 and 50? So in order to find the proportion of the population, they're trying to say how much of the population, if I was to translate this 40 into a z-score, translate this 50 into a z-score, which I can know because I have this normal population, and then I was to show this on my standard normal chart once I have their z-scores, how much of the population lies between those two values? Now, I can't look at the chart, which is the final step I need for this problem, until I've translated both 40 and 50 into relevant z-scores. So let's write that out. Z-score for 40 Okay, by now, do we know the formula for z-score? It is z-score is data value minus mean divided by standard deviation. So for this problem, I've got 40, that's my data value, minus the mean of 47, divided by the standard deviation of 3. That is negative 2.33 to 2 decimal places. Okay, next we need z-score of 50. Z equals 50 minus 47 divided by 3. That's a z-score of 1. Okay, so if I'm marking this on the graph, negative 2.33 is quite on the negative tail. So negative 2.33 is a z-score. We know at the peak is 0, so a z-score of 1 is over to the right. And I want to know how much of the total area, remember the entire curve has area under the curve 1, how much of that proportionally is in this middle section that you see shaded in red? Well, we know how to find the proportion of area between two values. It's just the proportion to the left of the larger value minus the proportion to the left of the smaller value. We did this earlier in the video. So all I've got to do is find the area to the left of negative 2.33. I need to find the area to the right of 1, and then subtract those two values. We'll use our chart for both of these. Okay, so for negative 2.33, I've got my negative 2.3 row, my 0.03 column, that's an area of 0.0099. Okay, next I need to go to the positive part of the chart to find area to the left of 1. 1.0 row, 0.00 column, 0.8413. Okay, so then the area between the curves is larger value, 8413, minus smaller value, 0.0099. Calculating that, and we will get 314. Okay, next question. What's the probability that the randomly chosen value will be less than 40? Now, this is a really nice problem because it actually is asking us a question that we already solved in the process of answering part A. In the process of answering part A, we found the proportion less than the z-score associated to 40, because remember, 40 had the z-score of negative 2.33. That proportion is 0.0099. So we can just record that, no additional work is needed. Okay, what is the probability that a randomly chosen value will be greater than 50? A little extra work is needed, but not much, because in part A, we already found for z-score, for 50, the z-score is 1. We found the area to the left is 0.8413. Now they care about greater than. So the area greater than that is the total value is 1 minus the piece that we don't want. And we'll get that value when you type in the calculator, 0.1587. So here in this next problem, pause the video, attempt it on your own, unpause to check your work. So here I've got a sample size of 16 will be drawn from a population with a mean 6, standard deviation 3. Is it appropriate to use a normal distribution to find the probabilities for X bar in this case? Okay, so here, this has to do with sample size. If you look at the sample size 16, we had a cutoff. In order for the central limit theorem to apply in this situation, our sample size needs to be greater than 30. So in this case, we would say no, sample size of 16 isn't large enough because we need the sample size to be greater than 30 for us to use a normal distribution in this case. Now B says if it's appropriate, find the probability that X bar will be greater than 4. This is not appropriate because of part A. We can't use a normal distribution, our sample size is too small. Similarly, it says if appropriate, find the 20th percentile. Again, not appropriate because in this case, both of these would rely on using the normal distribution as an approximation, which we just can't do because of the small sample size. So for the next problem, Attempt it on your own, unpause to check your work. So here we've got that a sample size of 8 is drawn from a normal population. And that is our key phrase here. This is not a sample of just any old population, it's a normal population. The mean is 42, the standard deviation is 4. So for A, when it asks you, is it appropriate to use a normal distribution? Yes. Even though our sample size still doesn't meet the greater than 30 threshold, since it's from a normal population, we don't have to get to a certain size of sample. If you're sampling from a normal population, any value is okay. It's just if you're sampling from an unknown population that you have to hit the threshold of greater than 30. So let's record that for A. Okay, so now is it appropriate? It is appropriate because we can use the normal distribution. Find the probability that X bar will be greater than, and in this case, I have an error here. If y'all would correct 30, after looking at this, I meant to type a different value. This is a typo. Let's all correct our problem. If you pause the video and attempt it on your own, you might have got some weird values. Sorry about that. Let's just kind of correct your work from there. So in this case, my z-score, when I'm trying to use it to find the probability about X bar, keep in mind my z-score formula for this particular case, because I'm dealing with X bar here, is X minus the mean for X bar divided by the standard deviation for X bar. Now, what is the mean for X bar, the standard deviation for X bar? You can look back in your notes from this section. The mean for X bar happens to be the mean, which in our case is 42. The standard deviation for X bar is the standard deviation of the sample divided by the square root of the sample size. So for us, that will be standard deviation of 4 divided by the square root of 8. Okay, and if I round that to maybe the first 4 decimal places, that's 1.4142. So now for my corrected value of 40, remember that was an original typo. We've corrected it to 40. Perhaps a later version of these notes, it will already be corrected to 40. So you might not need to make a change there. Our z-score is 40 minus 42 divided by my rounded version, 1.4142. Typing this into the calculator, and we get negative 1.41. Now remember, the z-score is just part of the way done. We now draw my standard normal curve. My z-score negative 1.41 would be here. I want to find the probability based on the phrasing that I'm greater than. Greater than is area to the right. Now I know the chart only gives me area to the left, so whatever I find, I'm going to say 1 minus that number from the chart. Now let's bring up our chart and find what is this area to the left that we don't want, so that we can then turn and make that the area to the right. So here I've got my negative 1.4 row, my 0.01 column, and I see the area to the left is 0.0793. So area to the right is then 1 minus 0.0793. And when you type that in the calculator, you get 0.9207. So continuing to part C, it says, if appropriate, which it is because we've got our normal population, find the 42nd percentile of X bar. Now, what does the 42nd percentile mean? If I've got my standard normal curve, the 42nd percentile is up to that z-score, of which you've got 42% of the total area enclosed into the curve. Now, what that means is we know at exactly the peak, I've got 50% of the area. So if I'm looking for 42%, I'm clearly to the left of the peak. So I'm just going to kind of draw my value here. I don't know this z-score yet. That's what I'm looking for. But what I do know about it is that the area before it accounts for 42% of the total. The total is 1. 42% of 1 is 0.42. Okay, now I've got the area. I'm looking for the z-score. This is the reverse of how we normally use the chart. So I'm going to look in the middle section to say what value is closest to 0.42, and then from that, get the z-score that we're looking for here. So let's just glance at this chart and try to find the value closest to 0.42. Looking through the values, it seems like clearly the closest comes here, 0.42. If you keep going, you get 0.41. If you go back, you get 0.3483. This corresponds to negative 0.20. And keep in mind that is my z-score. Now, if I'm wanting to find the 42nd percentile of x-bar, I want to know what is that data value x that created the z-score. So my formula is z-score is data value minus mu of x-bar over sigma of x-bar. Well, here we know that the z-score is negative 0.2. We knew previously that our mu of x-bar was 42. We knew that our sigma of x-bar when rounded was 0.1412. So I can set up this equation and solve and isolate for x. Remember, x is the data value. That, when translated to a z-score, is the 42nd percentile of the data values. So here I've got my negative 0.20 equals unknown value of x minus 42 divided by 1.4142. Now I need to use algebra to solve for x. In this case, I'll multiply both sides by 1.4142. And when I do that, let's see, negative 0.2 times 1.4142. That gives me negative 0.28284 equals x minus 42, because when I multiplied both sides by 1.412, that canceled from the denominator. I then add 42 to both sides to isolate x, and I get that data value, add 42, is 41.71716. So for our next example, attempt parts A, B, C, D, and E, and then unpause the video to check your work. Okay, let's zoom into parts A and B first. So our example states it was reported that in a recent year, 5% of employed adults in the U.S. held multiple jobs. A random sample of 75 adults is chosen. So here my sample size N is 75. As I gather more information, I'll start writing things down as well. Is it appropriate to use a normal approximation to find the probability that less than 6.5% of the individuals in the sample hold multiple jobs? If so, find the probability. If not, explain why not. Well, we don't know anything about our sample. It didn't say that it's coming from a normal population, so we can't assume it's normal. So the only way that we can use normal approximation would be if our sample size is large enough that the central limit theorem applies. Now, what is the cutoff for the central limit theorem? It's 30 sample size. And that would be in the general case. I need to correct myself for a little bit. That is the general case for when we can apply that to x bar. However, here, if I read this more carefully, I can see that I'm dealing with proportions because I've got my 5% here. I got my 6.5% here. This is asking, does the normal approximation apply to our proportion measurement? And if you look back in our notes, the central limit theorem for when you can use normal approximation for proportions has two things you have to check. What are those two things? Well, it's that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay. Now, p comes from your population proportion. My population proportion is p is 0.05 because that's talking about the percent of employed adults in the United States holding multiple jobs. Now, the 6.5, the reason it comes to play, it's a proportion of my sample. So that's going to be what we'll later call our p hat, 0.065. Remember, when you're dealing with proportions, you change the percent to a decimal. So then to verify this, I say my sample size of 75 times my p-value, 0.05, And for us to use a normal approximation, both of these must be true. So if even just one fails, that's enough to say, no, it doesn't apply. So here, this is 3.75, which is definitely not greater than 10. So this first one fails. Now, if we want, I can just check the other. I don't need to, because if one fails, it doesn't apply. But just for thoroughness, 75 times 1 minus 0.05, that's going to be 75 times 0.95. And that's 71.25. That is greater than or equal to 10. But we've already got a failure on the first one, so we would say this is not appropriate to use the normal approximation for this proportion measurement. Okay, let's read B. It says a new sample of 350 employed adults is chosen. What does that do? That increases our value of N. N is now 350, as opposed to the original 75. So now that we're at part B, the sample size is now 350. Find the probability that less than 6.5% of the individuals in the sample hold multiple jobs. Well, again, I can't find the probability that less than that sample proportion hold multiple jobs unless I know I'm working with an approximately normal curve so that I can then use our chart information. To check if it's approximately normal, we need to repeat our process from part A, but with my new sample size value. 350 times the population proportion of 0.05. I need that to be greater than or equal to 10. 350 times 0.05. That is 17.5. That's greater than or equal to 10. We're good so far. I need to check both. They both must be true. 350 times 1 minus 0.05. That's 350 times 0.95. 332.5, clearly greater than or equal to 10. The fact that both of these are correct tells me that I can use normal approximation. And once I can use normal approximation, I've got access to very strong tools in my cumulative distribution chart, my z-scores. Now, this is a normal approximation for a population proportion. And when we're dealing with a normal approximation for population proportion, while I'm looking for a z-score, the formula is not the same as what we've seen before. Instead, if you look back in your notes from this section, the z-score is the p hat, the sample proportion, minus mu of p hat divided by sigma of p hat. Now, what is mu of p hat? Well, mu of p hat is just my population proportion of 0.05. Okay, what is sigma of p hat? Sigma of p hat is the population proportion p times 1 minus p over the sample size n. So for this particular problem, my z-score is my sample proportion, which is 0.065, minus my mu of p hat, which is our population proportion, 0.05, divided by the square root of 0.05 times 1 minus 0.05 divided by the new sample size. Remember, the new sample size was upgraded to 350. And now to complete this, we'll need to be careful that we type this into our calculator without error. When I type this into the calculator, this is what I get. Remember, if you've got a z-score, you're using the cumulative normal chart. It's to 2 decimal places. So I'm just going to immediately round this to 1.29. So I've got my z-score associated with this sample proportion. Now I want to know the probability that, here you have to pay attention to these small details, less than that value. So if I've got my normal distribution, here's my z-score of 1.29. Am I interested in the area to the left or the right? Well, since it said less than, I'm interested in area to the left, which luckily for me is exactly from the chart. Let's look at our chart for our cumulative normal distribution here. So I'm looking for positive 1.29 as my z-score. So here I've got my 1.2 row, my 0.09 column. Zooming in, that's 0.9015, 0.9015. And that is the probability that less than 6.5% of the individuals of the sample hold multiple jobs. Okay, find the probability that more than 6.5% of the individuals of the sample of 350 hold multiple jobs. Well, since my sample size is the same, my sample proportion is the same, I know that the work to find for this sample proportion, the z-score, would lead me exactly to this answer. The only difference between B and C is instead of less than that population or sample proportion, I now want more than. So I want this value to the right. Well, we know that the total area is 1, so 1 minus the portion I don't want, 1 minus 90.9015, will give me a value of 0.0985. So we got part C mostly from the work that we had involved in part B, just a small extra step. Now for part D, it says find the probability that the proportion of individuals in the sample holds a multiple jobs is between 0.05 and 0.10. Keep in mind this 0.05, it's not phrased the same way as our 6.5% before. All it's doing here is doing our initial step of translating what we saw. You know, the previous question started with saying 6.5%, but what do we immediately do for that 6.5%? We change it to a decimal. So here in part D, they're just giving us the decimal straight away. This could have been phrased as find the probability of the proportion of individuals in the sample that hold multiple jobs is between 5% and 10%. But as a quick shortcut, they said, look, we're already giving you the percentage as a decimal. So don't be thrown off in the difference of why are we talking about percentages in B and C but not in D. It's just that the percentage has already been translated for you in D, whereas in B and C you had to take that extra step. So sadly, 5% and 10%, 0.05, 0.1 are not values that I've already worked with, so I kind of need to redo what we saw in step B now for step D for both of these values. Because we know when they're asking for proportions between, I need to find the z-score associated for both and then find the area to the left of both and say area to the left of the larger minus area to the left of the smaller. So in this case, for my sample proportion of 0.05, I'll do the work there. Sample proportion of 0.10, let's zoom in a bit. I've got my same z-score formulas from before. So I've got the z-score is now my new value, 0.05, minus the mu of p hat, which we saw was 0.05, divided by the square root of 0.05 times 1 minus 0.05, all divided by 350. Now, 0.05 minus 0.05, the top is 0. And if the top is 0, so long as the bottom is not 0, which it isn't, the overall fraction is 0. Type it into your calculator, you'll see that's true. So here, this is my z-score. Where is 0? It's exactly at the middle of the curve. And I don't even have to look at the cumulative normal chart because I know the entire normal curve, standard normal, has an area of 1. So half of that is 0.5. So the area to the left of this is 0.5. We could also see that in the chart if we wanted to. Let's do the new calculation for the sample proportion of 0.10. That z is equal to 0.10 minus 0.05 divided by the square root of 0.05 times 1 minus 0.05 divided by 350. Okay, type this in the calculator, round to 2 decimal places. If you do it, pause and verify if you haven't already. You get 4.29. Okay. Now I've got my z-score 4.29. Far to the right. Let's bring up our chart and see what area is to the left of that. So here in my cumulative normal chart, it tells me 3.7 or more. The area to the right is 0.9999. So to find the area between, it's the area to the left of the larger z-score, 0.9999, minus the area to the left of the smaller z-score, which in our case is 0.50. Subtract those and we get 0.4999. So at this moment, before we go to part D, I just want to check. Use this as an opportunity to check your understanding. Did you get B? If so, great. If you did get B, let's check the next things. Did you see how C was kind of a corollary because it used the same sample proportion, but it just wanted more than? So we were able to use our understanding of the standard normal curve and say, hey, if I know the amount less than this value, then the amount more than is just 1 minus that. Okay, now if you understood B and C, let's check D. Does it make sense, seeing the solution worked out, that D is the same process that we had to go about in B, but just for different population proportions? The difference is, sample proportions. The difference is, for D, I cared about my sample proportions of 0.05 and 0.10. And even though my mu of p hat and my sigma of p hat were the same, and I had to calculate a z-score, I got different z-scores because I was dealing with a different sample proportion. Once I got the z-scores, I used my cumulative normal chart to find the proportion of individuals less than those two, which then finally I synthesized the problem and said, okay, well, if you want to find the proportion between two z-scores, I know you always, if you can find the area to the left of both of them, say area to the left of the larger minus area to the left of the smaller. Okay, now that leads us to E. Would it be unusual if less than 4% of the individuals in the sample of 350 held multiple jobs? Now, this phrase of would it be unusual, that has a particular meaning in our class. That means, is the probability that this occurs, whatever we're interested in, is less than 0.05. Because if it's less than 0.05, it is unusual. If it's greater, it's not unusual. So this problem, through the phrasing of is this unusual, is asking us to connect the idea of, well, I know I judge unusualness in this class by is the probability that this event occurs less than 0.05. So part E is asking us to calculate the probability that less than 4% of the individuals in the sample hold multiple jobs. What is this 4% value? Of all the variables that we've named in this problem so far, 4% represents which variable? 4% represents a new sample proportion, a new p hat. 4% can be changed into the decimal value of 0.04. Where does p hat come into play? We use p hat in our z-score formula, along with mu of p hat, sigma of p hat. That gets us our z-score. Once we've got our z-score, we use our standard normal cumulative distribution chart to figure out the area of the curve that lies before that z-score. That is the probability that less than 4% in the sample hold multiple jobs. So that's outlining our process here. We're going to use the same formula as before because it's the same sample, and we've got our same mu of p hat, same sigma of p hat. It's just that p hat itself has changed. So my z-score is 0.04 minus my mu value of p hat, which was 0.05, divided by my sigma of p hat. Well, what was sigma of p hat? It was p itself, 0.05, times 1 minus 0.05, divided by 350. Remember, all of these come from formulas within our previous note sections. Now I know z-scores are rounded to 2 decimal places. Calculate this, and you'll see that you get negative 0.86 rounded to 2 decimal places. The chart automatically gives you values to the left, which, let's check our phrasing. It said less than, so we do want to the left. So what we get from the chart will be our exact answer. Let's bring up the chart. Okay, negative 0.8 row, negative 0.06 column, and I get 0.1949. Now, that is the probability. I still need to answer the question, is that unusual probability? Well, we know the cutoff for unusual is being less than 0.05, but 0.1949 is greater than 0.05. Because it's greater than the unusual cutoff, we say it is not unusual. So don't forget to tie that problem together. Now, as we conclude this video, I just want to verify, remember, this review video is meant to help you check your understanding after you've studied these sections individually. If any of these sections were confusing to you, and you can see the sections for each problem in our timestamps below of this video, go back to that specific section video because we have a much more lengthy and detailed discussion about how you solve this problem. In this review video, we're just checking our understanding, assuming we've reviewed those topics. So if you feel you need more help, don't rewatch the review video until you go back to that particular section video for our class and review that information. So as always, I'm happy to help you. Reach out to me via our campus communication if you have any questions.